series. Something we're trying to do here is give people an opportunity to branch out outside of their normal connections, normal technical skills, and also we're going to throw some soft skill presentations in here too. Coming up, we're going to take a break over the summer, and we're going to pick back up probably this August or so. I'm going to try and get a little bit better about sharing what the curriculum is for the upcoming year, see if anybody else wants to get involved. Today we got Cathey here with Georgia Transmissions, and he's going to teach us a little bit about electrical utilities. Hope you guys walk away with something new. Thank you guys. Welcome Joseph to the stage.
A round of applause. Thank you, Austin. Appreciate it. Like I said, I'm Joseph Cathey. My current role is I'm a supervisor of substation design at Georgia Transmission Corporation. I'll kind of talk more about what that is, but I'm curious with the audience here today, what industry are we in? Are we engineers, developers? Yes. Shout it out. Who do we work for? I know Austin's an engineer. What else we got? Architect. Okay.
Architect.
Survey. Awesome. Okay. So has anybody had any interface with electric utilities on projects? What's the consensus? Are we happy with it? Annoyed? Frustrated? All of it?
Depends on the day. Depends on the day.
Yeah. So,
Depends on if you're dealing with Georgia Power.
yeah.
And the person.
Yeah. So it's kind of one of those things where, it's a third party that's not really involved, doesn't really have a huge stake in your project, but you're very reliant on them, right? So hopefully today I'll kind of talk through some key things that you can do to help that go more smooth. And then just kind of talk about utilities in Georgia, kind of know what your options are. And so let's get into it. I'll do a quick introduction. So just got to show my little kid off. I got a 10-month-old. There he is. I went to Georgia Tech, and yeah, he's the best. I went to Georgia Tech and got a civil engineering degree. Go Jackets! And then went straight from getting a civil engineering degree to working for a power utility. So a lot of people think that's kind of weird, right? They think electrical engineers do power. There's actually a lot of all disciplines of engineering in utilities. I started off in substation design, mainly focused on structural. Did a lot of steel design, holding up all the bus work in a substation and working with transmission line, tensioning, all kinds of stuff like that. Then I went into transmission planning at the same company. There I dealt a lot with load serving projects, actually got to interact with the developers, mainly on large load projects. I did a steel smelting facility that was about 500 megawatt peak load. Data centers, obviously. Some weirder ones, Jack Link's beef jerky. They had a facility that we did an interconnection with. And the weirdest one, a primate testing facility in the middle of nowhere in South Georgia. So if you want to know where Planet of the Apes is going to start, I can show you on a map. And currently, like I said, I'm the supervisor of the design group, so I went back to design. And mainly I send emails all day. And so what we're going to talk about today, I'm going to kind of do an overview of electric utilities in Georgia. I'll start with kind of the history of electricity in Georgia and hit that at a 1,000-foot level and kind of explain how the history of Georgia rolled into what it looks like today. Then we'll talk about commercial development and the interface of electric service. And then I think it's important to talk about what I'm seeing in the industry today, because it's like anything I've ever seen. Just huge explosion in utility space. A lot of data centers, obviously, but even more than that. We are, I want to say 4x what we were 4 years ago. So our capital budget has gone up 4 times what it was. So tons of work. Don't have the necessary the necessary people that know what they're doing to do it. So we're hiring if anybody's looking for a career change. But we'll talk about that. And then if I have enough time left over, I just got some cool pictures at the end of projects I've worked on and things that y'all might find interesting. So, sound good? All right. So I'm going to try not to use too many acronyms. The utility industry speaks in acronyms, and it drives me nuts because nobody knows what anybody's talking about. So if I say an acronym and you don't know what it means, just ask. But the main thing that I'll be saying today is talking in watts. Watts is a measure of power, and mainly I deal in kilowatts and megawatts. The kind of diagram on the right is just common appliances and what their power consumption is to give you a scale. And then when I say kilowatt hours or megawatt hours, that's a measure of energy use, right? So you're seeing that on your power bill when you get frustrated with your kids for running the AC all summer long. That's what you're complaining about, is the kilowatt hours. That dollar figure right there, that's Georgia Power's average residential rate. It's just over 15 cents per kilowatt hour. And just an example, if you run a 3 kilowatt AC unit for 8 hours a day, that's 24 kilowatt hours. So that all makes sense? Good. And if I say kVA or MVA, that's more of a utility term than kW or megawatt hour or megawatt. It's basically the same thing. We're going to assume the power factor is at unity today, and we don't have any reactive power. So, all right, let's talk about the history of electricity. So, obviously, electricity wasn't invented, right? It's always existed, but it first became kind of commercially viable and something that the average consumer could use in the late 1800s. It all started in New York City. There's a great book called, what is it called? I wrote it down. Empire of Light. It's a great book. It talks about how Tesla and Edison were fighting each other to kind of control the electric market back in the late 1800s. Tesla was a proponent of AC, or alternating current, and Edison was a proponent of direct current, right? Obviously, alternating current won out. That's what we use today. So Tesla's idea was a little more economical. And it's kind of interesting that Tesla cars are ran off DC batteries. So that's kind of he named it wrong. He should have named it Edison, but I guess Tesla sounds cooler. You got a picture up here of a power generation house from the 1800s. You can see the safety issues there, right? Basically exposed generators running. At chest level, you could reach out and touch it. So it's not how they're built today, but that is actually one from Atlanta, right? When it's one of the first generation powerhouses in Georgia. 1884, power started coming to Georgia through Atlanta. And then all these companies are kind of the predecessors of Georgia Power, right? So it started out as Georgia Electric Light Company of Atlanta, and they started out with 22 street lights back in 1884. 20 years later, it grew and grew and grew. They changed their name to Georgia Railway and Electric, and they had a generation capacity of 94 megawatts, so grew quite a bit in 20 years. You might wonder, you hear railway, and you're like, well, locomotives existed way before then, right? Railway here is talking about streetcars. So they were powered with the electric running over them. They were connected to the wire, and they would get you around Atlanta. All right. And then by the 1920s, power was kind of pushing out to the other major cities in Georgia, Macon, Augusta, Athens. They were all starting to get some form of power to consumers. The bottom picture there, I think is really cool. That's your first edition of a bucket truck, right? They had a horse-drawn carriage with basically a ladder on top of it where they could get up on the poles and work on them. So if you're a nerd like me for electricity, you think that's really cool. 1,000. Yeah. Good question. Okay, so, and another context. So going back, 94 megawatts. That's roughly about 6,000 large homes today. At the peak load of a home, it's about 6,000 homes. Back then, a lot less, obviously, but today's standard home. All right, so we got the electricity to the major cities kind of across the country, right? There's a huge disparity to the rural communities. And kind of went through, we started pushing out power in the late 1800s. We're in the 1930s now, and only 10% of the rural communities across America had electric service. It was very slow to roll out, mainly because you had investor-owned utilities, right? They're not going to run power to 1 or 2 people per mile. It's just you're never going to make any money off that. So you had this huge disparity. Something similar to today, kind of like 10 years ago, is broadband. A lot of rural homes didn't have internet, or at least good internet. You have dial-up, Windstream, junk. So in the past 10 years, there's been a huge kind of similar push to get broadband out to rural communities. But back in the 30s, it was electricity. Again, only 10% of rural areas had it. And then FDR, going back to Georgia, so the Depression was happening, right? So he was trying to figure out how to save the American economy. The New Deal gave a lot of government funding to things. That created the Rural Electrification Administration, right? It gave a lot of funding to try to get electricity to rural communities. And FDR actually noticed the disparity when he came to Warm Springs, Georgia, to get in the springs for his polio. He was like, wow, nobody here has power. This is a lot different than where I'm from. So it's Georgia's mark on early electricity. And it worked, right? So in 50 years from where it started to 1930s, didn't hardly have anything in rural communities. And the next 20 years, it went from 10% to 90% of rural communities had electric service. The REA also was kind of the first thing that created electric membership cooperatives. So I'll hit on that later. I work for electric membership cooperatives, so I'm a big proponent of them. Does everybody know what that is? No? Okay, so EMCs, they're electric providers. They're all across the nation. We have 41 in Georgia, different electric distribution providers. They are membership-owned, community-owned electric providers. So they don't make a profit. They're not Georgia Power. They're not worried about the bottom line. They're there to serve their community the best way they can. So that's my spiel on EMCs. Any questions so far? All right. Cool pictures. So the top one is from South Georgia, where they were stringing lines. I don't know if anybody's an OSHA person, but I don't think that ladder meets OSHA these days. And then the bottom one is from Jackson County, when they were rolling electricity through there. All right, so that brings us to today. And here are your electric providers in Georgia. Okay, so you have the big dog, Georgia Power, right? Everybody knows them. And they are an investor-owned utility. You can buy their stock. They are emboldened to the Public Service Commission and their shareholders. So that's an IOU, investor-owned utility. Then the green circle, that's kind of the logo for electric membership cooperatives. They're all across the state. I'll hit on them more in the next few slides. Dalton Utilities is kind of a weird one. So anybody familiar with Dalton, the city in northwest Georgia? Mm-hmm. Yeah. Anybody have an idea of why they would have their own utility?
Carpet, Shaw.
Boom. So back when all this was kind of forming, they had these huge textile companies up in Dalton, right? So they're kind of a big player. They said, I want a piece of this pie. I want to be able to make my own decisions. So they created their own utility called Dalton. And then MEAG Power. Anybody ever heard of MEAG? No. MEAGs are your municipalities. So a lot of city-owned power is served through MEAG. They kind of own MEAG. It stands for Municipal Electric Authority of Georgia. And I'll tell you some ones that you've probably heard of. So this is your service territory map of Georgia. You probably think the red is Georgia Power, right? It's actually not. The white is Georgia Power. So if we're talking landmass here, Georgia Power really doesn't hit that much land in Georgia. They hit all the major cities. So they get a lot of customers, right? And you can kind of see they follow those interstate corridors where there's more people, right? Again, they're investor owned, so they're trying to make a profit. So white is Georgia Power. Red are your EMCs. They serve a bulk of the landmass of Georgia. That top left corner, that's where Dalton is. The orange, that's Dalton Utilities. Kind of that center one, that's orange as well. Those are two EMCs that are served on TVA, so a little weirdness there. And then your blues are your municipalities. So I'm sure y'all have heard of Marietta Power, maybe?
Real quick, I've heard of Georgia EMC, but they're not the power provider, are they?
No, sir. Georgia EMC is, how do I describe it? It's kind of their legislation arm. So all the EMCs own Georgia EMC, and they kind of go fight the battle on the legislative side for the EMCs. So municipalities, we got Ackworth, Marietta, Norcross Power, Buford. They all kind of own their distribution system in those cities. All right, and then we got some yellow in there. So anybody, and if you can't read that, it says unassigned. So anybody got an idea of what the yellow unassigned regions could be? Wind?
Or like territory dispute.
Competition.
They're on the march.
So
There's yellow in the middle, never mind.
it's actually a federal land. So the feds, they're not going to be constricted to their territories, right? They're going to get what they want. So really military bases. South of Columbus, you got Fort Moore now. It used to be Benning. That one in the bottom right corner, that's Okefenokee Swamp. So they kind of have their own cutout. Fort Stewart near Savannah, that's all the yellow ones. So, all right. So again, I got to hit on the EMCs because that's who I work for. There are 41 EMCs in the state of Georgia. 38 of them jointly own the company I work for, which is Georgia Transmission Corporation. We call it the family of companies, but there's a generation arm, which is Oglethorpe Power. There's a transmission arm, that's Georgia Transmission. And then Georgia System Operations controls and dispatches the generation and transmission system. So the 38 EMCs own the generation and transmission cooperative that I work for. It's one of the nation's biggest G&T cooperatives. We have about $20 billion in assets, and we own, I think, 450 substations roughly, and about 3,000 miles of transmission lines. So anyways, here's all your EMCs in the state. They serve about 50% of the population of Georgia and serve about 73% of the land in Georgia. So if you hadn't heard about EMCs, now you have. They're great. Big fan of EMCs. All right. So if you don't take anything else away from today, remember this slide. Okay. So remember I said you have your territories, right? Where if you're in that territory, that's your power provider. We are in a regulated market in Georgia, so that means that you don't really have a choice. If you're in that territory, that's your power provider, right? Except for one huge caveat. If your development is over 900 kW of peak connected load, then you do have an option to shop your provider. So please remember that. If you're working on a project, you're not happy with your initial power provider and you're over 900 kW, you can go shop it. And you can also kind of negotiate rates with different providers, and they can basically you get to pick who you want to work with. That 900 kW, there's a lot of caveats to it. A lot of litigation has gone on since 1973. But basically, let's say you have a development project and it's a huge subdivision. So each house, if you add them all up, it's over 900 kW. That does not apply to this, right? Because each one is individually metered, owned by a person. So it has to be one development, one facility. Does that make sense? Did anybody know that?
Input.
All right, so we get here. Does everybody understand what I was trying to say? You can choose your power provider if you're over 900 kW.
I assume that Publix is an example.
Yeah, oh, sorry. Good, yeah, thank you. Publix, the reason that picture's on there is Publix is about the smallest that gets you over 900 kW. So that's a reference.
Is that like the whole shopping center, right? Because Publix doesn't just go by itself typically.
Correct, yeah,
Okay.
yeah. So they'll have a master meter. That's considered one thing. And yeah, Publix, it's mainly the refrigeration and all that stuff gets you up there. And funny enough, before we got some really large load customers, Publix was actually the largest total consumer of EMCs in the state before some data centers came in, because they're kind of scattered everywhere. Everybody was getting that 900 kW.
So how does that work for a mall?
A mall would probably be a customer choice load, yeah.
I guess, are there incentives, I guess, when you have the choice, you know, if you're building this, you can say, hey, I've got options, maybe you get a better deal with the electrical.
Yeah, you know, you can see what they're going to offer you on a rate perspective, which is the most important, right?
Yeah.
What are you going to be paying? Sometimes they'll offer a 10-year incentive to get you there.
Free site lighting.
There you go. Yeah, they love putting up street lamps. And then it's also you're kind of a teammate, right? So you want to be working with the right people. Again, I'll just I guess plug an EMC, but you know, if you really like dealing with an EMC, you like the person that's responding to your outages, you might want to work with them, or Georgia Power. Maybe Georgia Power will take you to the Masters. You know. All right, so let's talk about commercial development and utility service coordination. So first thing, it's a critical path, right? In your project process, getting power to your site on time and how you need it is crucial, right? So when you're planning your project, when you're thinking through it, always be thinking, what coordination do I need to do with my local utility? And then get them involved as early as possible, right? You don't want to wait till you kind of have your whole site designed, you're ready to start construction, and then you're like, oh yeah, we need to talk to utility and get service here. It's really important to get them involved early, and then there's some points that are important to know. Your interconnection location, right? So where's your project going? And what are the local utilities around it? Do they have a small single-phase distribution line that's running by there and you need three-phase service? Are they 5 miles away and have to build to you? You know, these are all things that you need to kind of consider so you can give the utility time to make sure they meet your project timeline. Construction sequencing. So, you know, you start pouring concrete, pouring parking lots and everything else, and then you're like, I want the utility service underground. And they're like, well, it would have been a lot better if you could have let us dig it first and then poured it over it. I've seen that a lot. And again, I'm a transmission guy, but you know, they'll have this huge site campus that they've designed, and they want to stick the substation as far away from everything. Nobody wants to see it. They want trees in front of it. And the transmission line's on the very other side. And we're like, well, we got to build through this thing or go all the way around and like affect 20 property owners. You know, what were you thinking? You could have involved us first and we could have figured something out. And then a huge question I get is, can you go underground? going underground with high voltage transmission is very, very expensive, and most people balk when I tell them the figure. It's about 10x what overhead transmission costs. So we're 115 kV transmission line these days, overhead about $3 to $4 million a mile, depending on where you're at. So 10x that for underground, you're spending some money. Okay, so that's construction. Long lead time equipment. So I'm sure every industry has seen lead times go way out, right? It sucks. Things that could have taken 6 months 5 years ago take 18 months now, right? Same with the utility industry, if not worse. Even small things like pad mount transformers to serve small facilities, they could have a year-long lead time. Breakers like are shown here to give dedicated circuits, a year and a half. So if you don't get the utility involved and then you need a dedicated circuit, you might be waiting 18 months to get it to you. So as fast as you can tell them, and then will be, long lead time equipment is very important, and it's getting more and more.
What is more?
What?
What is more? Like, what is long versus average?
So like these distribution breakers, about 18 months lead time, and that's a very small piece. If you need a dedicated substation, high voltage breakers, I mean, 3 years. Yeah. Some are more. I'll show you some pictures when I hit lead time.
Is that the result of all this data center stuff happening in Georgia?
There's a lot of consideration. I got a whole slide I'll go over that says kind of what's going on. It all started obviously when COVID happened.
You got 10 minutes.
Okay, awesome. COVID obviously messed everything up on the supply side, and now we're seeing huge demand. So it's just hasn't stopped since COVID really. Another important thing to know when you're doing your project coordination is your loading and reliability requirements, right? What capacity do you need for your electric service? And then also your load factor, right? So how often are you going to be at that peak load, right? You might have a megawatt of connected load in your whole facility, but you're never going to be running all that at the same time, right? So it's a huge disservice to the utility, because if you ask for a megawatt of capacity, they're going to get that to you, right? But then you're spending a lot of money when you only use 200 kW peak, because you're never running everything at the same time, right? So it's important to know what your loading and your load factor is going to be. And then reliability again, the more reliable power you want, the more equipment you're going to need. More breakers, more relays, more protection schemes. So the reliability can really drive up the lead time and the cost. And then power supply contracts. So you obviously want to know what your power bill is going to be, right? So have those conversations with the utility early. Are there any upfront costs? Like I said, if you want underground service that's a mile at high voltage, you're probably going to have to cut the check for it. A utility would never make their money back to just let you do that, right? Data centers, a good example. We have asked for $50 million up front just to get service. And that's just an upfront cost, and then you hit the rate structure. So very expensive. All right, and then main point of this is if you're not aligned with all the stakeholders, then you're going to run into issues, delays, cost overruns. You need to get your owner's engineer and architects together with a utility provider. And then another one that kind of gets left off a lot is your local code enforcement, right? I want to loop them in at some point and be like, hey, this is the plan. You good with that? Is there anything we need to think about? Because you'd hate to get to the end of it and then your code enforcement's like, well, that's not right. So, any questions there? Okay. And then project life cycle. So planning, design, construction, I kind of already hit it on the last slide, but you need to kind of know what your load estimation is when you're planning your project. what your peak load could be, and then your load factor, your reliability requirements, what existing utilities are nearby. This was y'all familiar with greenfield versus brownfield? Y'all say those words? So greenfield's brand new, brownfield's a modification of an existing facility, right? We actually moved into a new office space, and we were going to put 20 EV chargers in our office. We went to the local utility, which is Georgia Power, and said, hey, we'd love to put EV chargers here. They said, yeah, your pad mount transformer's overloaded, your underground circuit's overloaded. We'll have to dig it all up, run the underground service. Be very expensive, take a long time. So we said, we'll wait on that. Not worth it to charge your car right now. Huh? Yeah. Okay, and then so that's planning. And then when you get into your design, your service entrance, which is basically your interface between where the utility hands it off and where your basically your design takes the electric service. So you need to make sure the utility and your engineers are kind of talking to each other, making sure the utility knows where to take it, what the demarcation point is going to be, right? It's always nice to have a safety, some kind of disconnect switch to have a demarcation point. So just making sure your design and the utility is on the same page. And then routing, I've already talked about it a few times, but make sure you don't build this beautiful, or you don't design this beautiful campus, and then you need to run a huge transmission line through the middle of it. All right, and then when you get to construction, coordination between your site construction and the utility is really important, especially when you get bigger and bigger. There's some data center sites I've been at where the general contractor gets very upset with the utility because the utility does their own work. The GC is trying to control the whole site, right? They're in charge of their safety and everything coming on and off site. And we're bringing in a 20,000 pound transformer on a trailer, or sorry, 200,000 pound transformer. Yeah. And then equipment delivery, like I said, we're bringing in huge poles, huge equipment. Your construction contractor needs to know about all that stuff, and then vice versa. The utility needs to know how to get in and out. And then commissioning and energization is a big one. So the utility is going to be doing a lot of testing at the end, as well as your electricians and electrical engineers in the facility. So they need to make sure they're coordinating and make sure everybody's being safe and not energizing into anything that they shouldn't be. All right, so I'm going to hit on large loads because that's kind of a huge topic with all the data centers going on, and that's mainly what I've worked on. So the bigger you get, the more complex it's going to be, right? The methods of service, which is how you get power to that site, get more and more complex the bigger you need. This is a picture of a data center substation that's serving just one customer, the data center behind it. And you can see how big that infrastructure is. I think they have 4 150 MVA transformers, so a lot of power. You can barely see it, but there's probably 30 breakers in here to meet their reliability requirements. It's a 1.5 breaker protection scheme, if anybody's familiar with that. So it just gets really complex the bigger you get. And then the impact to the power system is getting more and more. If you drop a huge data center, you might have considerations 50 miles from there where you're upgrading different transmission stations to try to get service to that. So it can take a really long time, and it's a lot of work on the utility when you are doing these large loads. And then another huge one that everybody hates is condemnation, right? So you got to route all these transmission lines. Eminent domain, everybody's heard that word, right? Utilities have the option to condemn property from people. GTC tries as hard as they can not to do that. We'll do anything we can not to condemn a property. But when you're working on a large load and the utility is building a transmission line just for that one customer, a lot of people are going to get mad, right? You've seen it on the news, I'm sure. People get mad that data centers are coming to their area. So if you are already iffy on data centers and then you have a transmission line going through your front yard, I can see how you get pretty mad. So it just eats up a lot of time in a project if you have to condemn people. And then your rate structure can be really complicated with large loads. A lot of things to consider on a power supply contract. Honestly, you probably need to get lawyers involved to make sure everybody understands what's happening on large loads. All right, so that's the development portion. Everybody good with that? Makes sense? Okay. How am I doing on time?
Just a couple minutes.
Oof, all right. So I'll quickly talk about the state of the industry. So 2021, after COVID, things started opening back up. You had this supply shock, right? The manufacturers of all electric utility equipment, pretty much everything in the economy, we just didn't have that supply side, right? When everything started opening back up. A lot of people had moved roles when factories shut down. It took a long time to get that supply back up. Well, last year, the utility industry specifically hit a demand shock where every utility is trying to upgrade their system all at the same time across the world, basically, but definitely the US. There's a lot of reasons for that are on a slide from now, but basically, take away from this, prices shot up and lead times shot way up, right? So you can see here, power transformers over 100% increase in price from 2020. So double the price of what it was 5 years ago. And these things are not cheap. And then this just shows kind of the market size. So in 2020, we were at about 25 billion in power transformers, and now we're at 52 billion. So that's the market increase of what's spent every year in the US. So basically doubled in price, doubled in demand. Lead times went way out. High voltage breakers, I've seen quotes 250 weeks. That's 5 years. How do you plan a project when a utility tells you 5 years for a breaker? So we're working through a lot of these lead time issues, a lot of demand issues. You can see here, just everything basically doubled with lead times. So why is that happening? Increased load. So large loads, data centers are a piece of it for sure. It's not the whole story. You've had a lot of native load growth. So housing has boomed, other industries have shot up the past 5 years. Our electric infrastructure has not really been upgraded like it should have been. We were always kind of slow, steady growth. You could kind of do your projects slowly, make upgrades as needed. We didn't want to spend a ton of money upgrading it if we didn't have to, right? And then basically since the 70s, we didn't see a huge jump in electric demand because every time you'd need more electricity, some efficiencies hit and it would kind of dip back down. Take the LED light bulb, right? Put LEDs everywhere, kind of the load demand kind of went down again. So over the past 50 years, we really haven't upgraded the system very much. And now everybody's trying to upgrade at the same time. Prices and lead times have just gone crazy. And then changes in generation and where the load is flowing to. This is a picture, you can see all the solar projects that just my company, we have a renewable arm called Green Power EMC. You can see all the solar projects that we've done basically in the past 5 years. They're all in South Georgia where the land's cheap and it's sunny, but that load has to get north to the load centers. So we're upgrading a ton of transmission to get it to more northern areas, basically Atlanta, right? Any questions there? I'm kind of flying through that.
When you upgrade your transmission lines, you just add another line?
Adding more or increasing the conductor size to get more capacity out of it. All right. Data centers, talked about them a lot already, but right now we have about 50 gigawatts A gigawatt is 1,000 megawatts, so ton of load. Wrote it down here somewhere. Okay, so we're going to have about 50 gigawatts, 50 to 70 gigawatts forecasted by 2035. So right now we're at 50, so we're either doubling or more than doubling for data center load in the next 10 years. So huge load growth. For scale, Vogtle 3 and 4, billions of dollar nuclear facility in southeast Georgia, took 20 years to develop, gave us 2.2 gigawatts. So that whole project was ate up by a couple data centers. So it's a huge concern in the utility industry is how we're going to get this generation for these large loads.
So it's a possibility that the project could be obsolete by the time you get what you need. Because you said that was 20, that took 20 years to do. It only produced 2.2, and we're going to go up further from that.
I wouldn't say they're obsolete because they're still going to be operational, but we just need way more. And if it's going to take 20 years to build a new nuclear site, it's not really feasible, right? So it's got to come from somewhere.
Something else other than nuclear.
Yeah. All right. So some things that I see that are going to kind of solve the problem. We're just going to build for the next 10 to 15 years. Like I said, our capital construction budget is about 4 times what it was 5 years ago. So we are going gangbusters on updating facilities. I think on-site generation for these large loads is going to be the next thing. They're going to build their own combined cycle gas generators. And then they're going to have some storage, I think, is another good solution. They're going to have batteries or some kind of storage on site so they can kind of help with that peak demand. And then load flexibility. So basically what that means is, can you curtail your power down during peak times? Utilities live on the peak, right? So if you can get that peak load down, you're going to save a lot of money. And data centers specifically, if they can go on to backup power generation during those few peak hours of the year, I think they'll make rate structures to where that's really incentivized. Let's see, smart grid. So we are putting fiber everywhere and connecting all the equipment. That's been a big push lately. Basically everything is going to be connected through fiber, so you can talk through relays instantaneous. And then it also kind of leads to having kind of a dynamic grid. So right now we rate our infrastructure based on like a manufacturer's rating, right? So it's good for this amount of amps at this temperature. What we're going toward is having a real world dynamic rating. So based on the ambient temperature at that moment, where it's at, can we push this grid more than what we said we could? So that's going to be a really interesting way to operate the system in the future. And then new technology. We have just started putting out high temp transmission line conductor. It's rated for 200 degrees Celsius. So you can get it really, really hot compared to the former ones. And it won't sag as much. You can run a lot more current through it. And it's basically a composite instead of, it's still aluminum around it, but it's a composite core that can get really hot. So those are some solutions that we're looking at in the industry to help solve this crisis. All right, so that is my presentation. Are we ending on time?
Yeah.
Okay.
Good job, man.
Thank you. And I had some really cool pictures, but I ran out of time. So. Y'all want to see it?
Yeah.
Okay. All right, so this is a data center project that I worked on. This is the substation that serves it. It is a breaker and a half scheme, so basically you can always have a breaker out of service, whether planned or emergency, and still serve it as you would normally. So a lot of pieces of equipment, a lot of relaying. One of these substations is going to run you about $80 million. So it is not cheap. I like this picture because you can see how big these transformers are. See the people in the bottom left corner? So that transformer is a 500 to 230 kV. So it's bringing in 500,000 volts, stepping it down to 230,000 volts. The capacity of it is 450 MVA. And it weighs almost 600,000 pounds. And it has 20,000 gallons of oil inside it. And what makes it even crazier is this is a single phase transformer. So if your power's in 3-phase, right? So you have 3 of these plus a spare. You have 4 of these transformers to step that voltage down.
And what does that cost?
One of those are about 35 million. So you're spending a pretty penny on just transformers there. And you have to have that 4th one because these are so big and heavy. It's not really feasible to get a new one there in an emergency situation. So basically they just pick it up and slide it to where the failed one went. And that's the best we can do. A lot of these you have to put on rail cars and get it as close to the side as you can and then close down the roads to move it to the site. So they're very, very big. Cool picture from South Georgia. I was planning down there. We caught a crop duster plane in our transmission line. It created a phase-to-phase fault and that went through the plane. You can see the broken pole hanging there still up in the air on the left side. But we caught it. The pilot was fine, and the fire department came and got him down. But it's pretty crazy. That's a helicopter stringing a transmission line. And you have somebody in a bucket truck kind of catching it as they pull it. This is a very effective way to pull transmission lines, especially across like bridges and elevation changes, because it's really hard to do it from the ground. So helicopters are a good tool to use. You can also do hotline work with a helicopter, and those dudes are nuts because they're hanging from a rope from a helicopter working on 500,000 kV or 500,000 volts. I wouldn't do that. Underground transmission line. So this is a 115 kV underground transmission line. You can see the conduit it goes in. I think that's a 8 or 12 inch conduit. I'm not sure. 8 or 10 inch conduit. Very expensive to do, and the actual conductor is the metal part there, and then the insulation is around it. And it's hard to tell the scale of that. The thing's about that big around. So it's very expensive, very, very big.
What's that backfilled with?
I don't think they backfill it with concrete. I think they just bury it. Yeah. There's not a whole lot of underground transmission lines in Georgia. There are some through Atlanta to the airport, actually, and it caught on fire a few years ago. I don't know if anybody remembers that. But all right, one really awesome thing on the generation side is the company I work for owns a pump hydro storage facility. So we built this mountain, or sorry, the mountain was there. We built the reservoir on top of it. So you can see it at the very top. This picture shows the scale of how big the reservoir is. 220 acre pond we built on the top of a mountain, dug it out. It's 50 feet deep. And then the generation facility is through the mountain. So there's like a 8-story generation built into the mountain. And then you can just see basically the parking lot at the bottom there. But it has these huge pipes and turbines in the mountain, and you drain the pond and it generates electricity. And it goes to the bottom reservoir, and then when you need to fill the water back up, you turn the generators around and it pumps it back up to the top of the mountain. And its capacity is just over a gigawatt of power that you can get from that. And it refills in about 7 hours. So these are huge tunnels. You can drive a truck through them when they're doing maintenance. They'll drive trucks through the tunnels. It's cool. Yeah. That's the best part about it is you can call on it immediately. There's no ramp up, nothing. It's ready to go. Potential energy is all it is, right?
So what do you use that for, peak times?
Yes.
And then you
Yep.
refill it during slower time.
Middle of the night. Yep. So this generation facility is actually a net energy user. It takes more energy to pump it back up than you get from running it down, which makes sense when you think about it. But again, they're living off peak time, so they'll drain it during peak and then middle of the night pump it back up.
So do you use the same energy that's generated? If you don't clear out all the energy during peak times, is that the same energy to pump it back up?
Now, your energy is going to go out onto the system. There's really no getting it back.
Oh, okay.
So actually, interesting caveat to this. So this actually makes nuclear a good bit more efficient because you can't turn nuclear off, right? Once you fuel it, it's running. So even in the middle of the night, you have your nuclear source running. You can use some of that power to bring the water back up to the top of the mountain. So solar is actually changing this to where sometimes you have so much excess solar generation on a really cold, sunny day that they'll distribute it later in the day, like when everybody's getting home from work, and then pump it back up in the middle of the next day, like at noon. So it's a very interesting facility. All right, and that is the last slide I had. So I appreciate everybody's time. I hope you got something out of it. If anybody has any questions, let me know. Thanks.